is his workout. This is not his VO2 max. But this is a very high number, which means he's very fit. If he's sustaining this, maybe this is 70% of his VO2 max. Let's do this. If this is 70% of his VO2 max, what's his VO2 max? How are you figuring that out? You're dividing 52.17 by 0.7. If you multiply 52.17 by 0.7, you're going to get a number lower than 52. Which if you're just absent-mindedly doing math, you'll just do and move on. But if you think about what you're doing, if 52 is 70% of his max, that means his max is higher than 52. So if you're getting a max lower than 52, you did something wrong. Okay, so what we're actually doing is 52.17 is 70% of what? What do I need to multiply by 0.7 to get this number? So we're actually dividing by 0.7. And what do we end up with? 74. Like that? That's a ridiculously high number, but that's because I just made up these numbers. Go ahead. No, I'm just making up numbers for the example, but this is something you should be able to do. If I say this person is running at 35 mLs per kg per minute, and this is 80% of their max, what is their max? That's something you need to know how to do. Yes?
So you said for training, their max could be 60. So on the test, are you gonna like look over what you input, and if like we get something like 70 or 80, would that be a red
Yeah,
flag?
this is possible. It's way above average, so this would be like a very well trained endurance athlete. This is possible. The 60 is average. So you could find an elite cross country athlete with a VO2 this high.
I get, yeah. I mean,
But yeah, I try to keep the numbers
okay.
pretty
But
normal on the
won't,
test.
You won't have an answer be like 98.
No,
Okay.
not on purpose.
Okay.
No. But it happens, as we saw with the
Yeah.
on the worksheet. Mistakes happen in the creation of these questions. Okay, any other questions on this? Yes?
Sorry, so the 74.53 is the, like, max?
This person's VO2 max. If 52 is 70% of their max, that means their max is 74. Go.
So, let's say like the person you're training, they had caffeine, and I know it really depends on the dosage and how if they have a sensitivity to it, but like, is there a way to account like a plus or minus?
There's not a number to put on it.
Okay.
Yeah, it's gonna be different for everyone. And yeah, the dosage of caffeine and how long ago they took it, but it is gonna elevate the heart rate.
Okay.
Somebody else have a question? Okay, so we're done playing with these calculations for now. Let's go back to the very beginning of this chapter when I talked about, I said, okay, we're going to talk about energy expenditure, which is calories. Calories are a measure of heat, right? And then I talked about direct calorimetry. Direct calorimetry is an attempt to directly measure your heat production, but we talked about the limitations of that with the treadmill producing heat and other things, and so then we started talking about indirect calorimetry. In indirect calorimetry, we're measuring oxygen consumption, carbon dioxide production, but then there's a known relationship between oxygen consumption and energy expenditure, so we convert. And we used that number to convert oxygen consumption to energy expenditure because we know that for every liter of oxygen you consume, you burn 5 calories. Remember all this? And then this took us down this rabbit hole of all these calculations. So, remember that I said this number is not exactly 5? It ranges somewhere between like 4.7 and 5.1, depending on what substrate you're relying on. So it's gonna change whether you're using more carbohydrate or more fat. We're not getting into the details of that, but the issue is how accurate this number is affects how accurate our calculations are. So it depends on the ratio of the oxygen we're consuming and the carbon dioxide we're producing. So the ratio between the carbon dioxide we're producing and the oxygen we're consuming is called the RER, which stands for respiratory exchange ratio. Respiratory exchange ratio is the ratio between the volume of carbon dioxide we are producing and the volume of oxygen we are consuming. Where is oxygen consumed in your body? There's only one place in the
Or just like
oxygen
the lungs.
in your body where oxygen is consumed. It's not in your lungs.
Oh, wait.
In the mitochondria, at the end of the electron transport chain, when it combines with hydrogen to produce water. That is the consumption of oxygen. Your lungs do not consume oxygen. Your lungs help you get the oxygen from the air into your blood. And then your blood delivers it to the muscle, and then the myoglobin delivers it to the mitochondria, and then it gets combined with hydrogen and consumed. Okay? There's a known amount of oxygen consumed when we're metabolizing fat or carbohydrates. We can count it. I do that in 446. I don't do it in here, but we can count how much oxygen is consumed from a molecule of carbohydrate or fat. We can also count how much carbon dioxide is produced. There's carbon dioxide produced within our metabolic systems. In the Krebs cycle and other places, there's a known amount. So there's a known ratio. Which substrate consumes more oxygen? Fat. Because fat requires oxygen for its metabolism, carbohydrates do not. So when you're metabolizing fat, the denominator of this ratio will be higher. What does that do to the overall ratio? Makes it lower. So the RER will be lower when you're relying on fat. The RER will be higher when you're relying on carbohydrates, because fats require more oxygen. RER ranges from 0.7 to 1. So if your RER is 0.7, it means you're using 100% fat. If your RER is 1, it means you're using 100% carbohydrates. Can we ever be using 100% fat? No, why not?
There's always going to be a mixed part of it that's using the carbs.
Glycolysis has to run at all times. So you're always using a little bit of carbohydrates. So 0.7 is a theoretical load for RER. We can never actually be at 0.7. When you're resting, that's when you're most relying on fat. Your RER when you're resting is actually like 0.8. It's as low as it gets in reality. And then as you increase your exercise intensity, you rely more on fast twitch fibers, which work anaerobically, and you start to rely more on carbohydrates. Does that remind you of the crossover concept? It should. So as you increase your intensity, you rely more and more on carbohydrates, RER approaches 1. The problem is, at high intensities, there's additional carbon dioxide produced outside of the metabolic systems. So there's a known amount of carbon dioxide produced in the metabolic systems that gives us this ratio. And this ratio is what determines the caloric equivalent. Okay? At high intensities, there's an additional source of carbon dioxide. That is from the bicarbonate buffer. Did we discuss the bicarbonate buffer last week?
No.
Okay. So we've mentioned the buffer before as one of the places we clear lactic acid. Okay, so that's what this is. This is the bicarbonate buffer. bicarbonate buffer is HCO3. It's produced by your body. Its job is to pick up the hydrogen from the lactic acid. Okay, so this is the bicarbonate buffer. This hydrogen is from lactic acid. So let's think real quick about the production of lactic acid. Why does lactic acid have a hydrogen in it? How do we convert pyruvate to lactic acid?
We reduce it.
When the NADH can't drop off its hydrogen electron at the mitochondria, it gives it to the pyruvate. When you give the hydrogen and the electron to the pyruvate, it creates lactate. So the lactic acid has hydrogen in it. And that needs to be cleared. That's going to cause fatigue. So the buffer's job is to neutralize that. It's going to pick up the hydrogen, and then it becomes H2CO3, which is called carbonic acid. HCO3 is in your blood.
Okay.
So when the lactic acid is produced in the muscle, it's shuttled into the blood. And then the buffer picks up the hydrogen.
So you know how lactic acid goes like the heart, the buffers, the
Yeah.
kidneys? So it's actually, does it stop at lactic acid, or does that also go to like the heart, the kidneys?
So the full molecule of lactic acid can go to the other places.
But that, the buffer will stop it before it does that?
No, some of it's still gonna go to those places and some of it's going to the buffer.
Okay.
Yeah, it's still being cleared in all the different areas. We're just getting more into detail on this particular pathway. Go ahead.
So going back to like chapter 2, I think you use like lactate and lactic acid interchangeably. Is there a difference between?
There is a chemical difference, but I'm just using the terms interchangeably. Yeah. Okay, so once we have carbonic acid, this is then going to split into H2O and CO2. H2O is water. That's a good thing, that's harmless, that can stay in our blood, no problem. Carbon dioxide is gonna go into your lungs so you can exhale it. Okay, so your expiration of carbon dioxide is helping clear the hydrogen from the lactic acid. But the problem is, this excess carbon dioxide is gonna drive this number unnaturally high. And that's gonna make the RER go above 1. So you might have an RER of 1.1 or 1.2, which shouldn't be possible. It's not possible with the carbon dioxide that's produced in the metabolic systems. So when the RER gets that high, it makes our calculations less accurate. Because this number, the caloric equivalent, is based on the RER. So if the RER is faulty, our calculations are less accurate. Okay, so to boil this whole point down, the main limitation of indirect calorimetry is that it's less accurate at high intensities because of the excess carbon dioxide produced from the bicarbonate buffer makes RER go above 1, which makes our calculations less accurate. I'll say that again. Main limitation of indirect calorimetry is that it's less accurate at high intensities. At high intensities, we produce a lot of lactic acid, so the buffer is working. Buffer produces carbon dioxide. That carbon dioxide is excess carbon dioxide that's not accounted for in the metabolic systems, and it makes the RER go above 1. And that just makes our calculations less accurate. You don't need to know the details of why it makes our calculations less accurate. You do that in 446. So this carbon dioxide, because it's produced outside the metabolic systems, like do we have carbon dioxide produced in the Krebs cycle? We call that metabolic carbon dioxide. I'll call this non-metabolic carbon dioxide. So at high intensities, we have non-metabolic carbon dioxide produced by the bicarbonate buffer, which makes the RER go above 1, which makes our calculations less accurate. Okay, another way to say this is that indirect calorimetry assumes that you're working primarily aerobically. Because it's when you work at high anaerobic intensities that this becomes less accurate. Questions on that?
What are like, so you said like 0.7 to 1.0, those are like theoretical numbers. What are like practical, is the 0.8 to?
0.8 to 1.2 in
Okay.
reality is the range, yeah. Other questions? Okay. Let's move on to a more fun topic. Let's talk about resting metabolic rate. Resting metabolic rate is how many calories your body consumes if you were to just rest for an entire day. Okay, if you stay in bed for 24 hours, you're still burning calories because you're still breathing. Consuming oxygen burns calories. So we're going to do a calculation to figure out how many calories a typical person burns if they stay at rest for 24 hours. Okay, the way we do that, we already have an estimate of resting oxygen consumption. How much oxygen does the typical person consume per minute at rest? 3.5 milliliters of oxygen per kilogram of body weight per minute is resting oxygen consumption. And we discussed how this applies to everyone, right? Because it accounts for your body weight. If we convert this to liters per minute, larger people will have a higher absolute oxygen consumption. But relative, this applies to everybody. If we take an average 150-pound person, resting, so consuming this much oxygen for 24 hours, an entire day, how many calories will they burn? Calculate energy expenditure. That's this. You know how to do that. See if you can figure it out. We need this in minutes, so the units can cancel out, but I gave it to you in hours. How do we figure out how many minutes are in 24 hours? Multiply it by 60. There's 60 minutes in 1 hour, and we've got 24 of them. So 60 times 24. And what do you get? 1,440 minutes in 24 hours. Okay, do this math and tell me what you get. 0.14. Okay, I'm not concerned about quarter of a calorie. Calories in a day. So, a 150-pound person who stays in bed for 24 hours will still burn about 1,700 calories. A 150-pound person who stays in bed for 24 hours will still burn about 1,700 calories. That's their resting metabolic rate. Michael?
So what does it mean if they burn more kilocalories per day or less? What does that mean about the person?
Well, we'd refer to that as having a faster metabolism. That probably means they have more muscle mass. I'm going to talk about that in a second. Right now, you can estimate your own resting metabolic rate. All you need is your weight. Plug your own weight in there and see what you get. Okay, does everybody have a number for themselves? Not yet?
26, 34. See, so that's like average.
I'm gonna talk about if you're outside this range. Okay, so everybody have a number for themselves. So, average resting metabolic rate is between 1,500 and 1,800 calories per day. So you can see 150 pounds is considered average. That number falls right in the middle here. Some of you are in this range. Some of you probably fall below this range. Some of you are probably above this range. This is average. What determines this number is two main things. One is muscle mass, because muscle is metabolically active. It burns calories at rest and fat does not. Okay, this number that we're plugging in here, kilograms, does not distinguish between muscle and fat. So this is why this is an estimate. But this is going to give you, the more you weigh, it's going to give you a higher resting energy expenditure. That's why your number is higher, because your weight is higher. Okay, but in reality, muscle mass is going to give you the highest resting energy expenditure. People who are large because of fat have the next highest resting metabolic rate, because the larger a person is, whether they're large because of muscle or fat, the larger a person is, the more surface area they have, and therefore they lose more heat. So the body has to work harder to thermoregulate, and that burns calories. So the highest resting metabolic rate are people who are large because of muscle. The next highest resting metabolic rate is people who are large because of fat. And then the smaller you get, the lower your resting metabolic rate. Okay, so that should explain where you sit in this range. Yes?
So, if someone weighs like 185, they're gonna be outside that range. Does that just mean 185 is above average weight for somebody?
150 is considered average.
Average weight overall for the population? How about?
Yeah, that's probably different now than it was when we started using this number.
Yeah, I was gonna say,
Yeah, it sounds a little low for now, but we still use it. Okay, now let's say this. If I were to have you take your heart rate right now, we would consider it a resting heart rate because you've been sitting down for well over an hour. But it's not a true resting heart rate, right? You probably ate something today, which increases your heart rate. You probably had some caffeine, which increases your heart rate. Maybe you're stressed about the math, which increases your heart rate. Okay, so although we consider this a resting heart rate, it's not your true lowest. So same thing for this resting estimation. This is not a true lowest that your metabolic rate can go. The true lowest that your metabolic rate can go is called your basal metabolic rate. Basal metabolic rate has to be measured. Resting is an estimate. Basal is a measurement. And in order to make this measurement accurate, you have to meet some criteria before you do the test. You have to, first of all, get 8 hours of sleep. Good luck. Then you have to fast for 12 hours because digestion increases your metabolic rate. Then you have to lie supine in a dimly lit, thermoregulated room for an extended period of time so we can get you as relaxed as possible, slow down all of your body processes. And then we put a mask on you and hook you to the metabolic cart and measure your actual oxygen consumption. So it's more accurate than the 3.5 estimate. And it's more accurate than the body weight readings, actually measuring your oxygen consumption. So average basal metabolic rate is somewhere between 1,200 and 1,500 calories per day. So typically a couple hundred calories less than what we estimate as resting. Costs a lot of money to have that test done. So you can do this estimate of your resting and safely subtract about 200 calories and have a pretty good estimate of your basal. Okay, that's an important number to know or have an idea of your basal metabolic rate, because that is truly how many calories your body requires to survive for 24 hours. Your basal metabolic rate is how many calories your body requires to survive for 24 hours. Which means if you consume less than that, you're starving. You're not eating enough calories to sustain life in your body for 24 hours. That's starving. What your body does in that situation is it will hold on to its fat stores. It will protect you from breaking down your fat. And it will break down your muscle instead. So, if somebody has a goal of losing weight, and I always clarify that by saying their real goal is losing fat, and their strategy is to hardly eat anything, if they have a basal metabolic rate of 1,500 calories, but they're only eating 1,000 calories, they're gonna lose weight, but they're gonna lose muscle, which is never the goal. Okay, so the trick for fat loss is you have to be eating enough to allow your body to do fat metabolism. And this is the trap a lot of people fall into by eating too few calories. And you're gonna lose weight, but you're gonna lose muscle. Okay.
Can you repeat what you said for BMR? So it requires your body to consume that amount of calories?
Your BMR is how many calories your body requires to survive for 24 hours. So if you're consuming less than that, your body is going to protect your fat, not break it down, and instead break down muscle for energy.
So what happens if somebody doesn't fast?
So if you're fasting, it depends how long you're fasting for.
What if you're like on a 5-day fast?
How strict is your fast? What are you intaking?
Uh,
No calories at all?
No, no calories.
No calories at all.
Water.
Okay, so if you go on a complete water fast for a week, you're gonna lose a lot of muscle. A lot of muscle. All you're doing is looking at the number on the scale, oh, I've lost weight, good for me. Scale's not telling you what you lost. Okay, people who fast, like, I think Ramadan is going on right now, isn't it? So I believe for Ramadan you fast for 12 hours, but you can eat during the other 12 hours. So from the research I've read, people who follow that protocol typically end up eating the same number of calories in a day as they would when they spread out their food over the day. So that's not gonna make that much of a difference. But if you're not eating, if you're only drinking water for 5 days, you're definitely losing muscle, which is probably not your goal. Go ahead.
Is it healthy to eat that much food in like a small period of time and then stop eating?
If you're only doing this, I don't know how long Ramadan is. It's not gonna be a big deal.
Different for like a 1-day fast or 2-day fast.
I mean, let's say this, if you go 24-hour period and eat nothing, and your body burns 1,500 calories, if we're talking about fat, that's half a pound of fat. And probably, I mean, not a whole lot of muscle. It's not gonna make that big of a deal for a day. Okay, so here comes again the thing for if someone's trying to lose weight, if they're trying to lose fat, you need to be in a negative calorie balance, meaning you need to be taking in fewer calories than you're burning. Okay, average person, I haven't given you this number yet, but average person burns about 2,000 calories in a day, because we're not sitting in bed for 24 hours, right? We're getting up and moving around. So average person burns about 2,000 calories in a day. If this person wants to lose weight, typical deficit is a 500 calorie a day deficit. That gives you a 1 pound a week of fat loss, which we're gonna talk about again later in the semester. So if they burn 2,000 calories a day and they wanna be in a 500 calorie deficit, they're eating 1,500 calories a day. And they're safe at that because they're at their basal metabolic rate. But that's not a whole lot of food. So if this person who wants to lose weight wants to eat more than 1,500 calories and still lose weight, they have to increase this total number of calories that they're burning, meaning they have to exercise. So if you add a 500 calorie workout to this person's day, now they burn 2,500 calories in a day, they can eat 2,000 and still be in a 500 calorie deficit and lose weight and be above the BMR. But good idea to have an idea of what this basal number is because you do not want to eat fewer than that. if you wanna sustain your muscle. Go ahead.
And so if you burn 2,500, is it still okay to only eat 1,500? Like what happens if you're just burning more fat?
Yeah, so if you're burning 2,500 calories in a day and only eating 1,500, that's a 1,000 calorie a day deficit, which is 2 pounds of fat per week. Can't do a whole lot more than that. So, we're gonna talk about this, is gonna come up again later in the semester, but if somebody's losing more than 2 pounds of fat, if somebody's losing more than 2 pounds per week, they're losing muscle. Because it's almost impossible to be more than 1,000 calories in deficit and not go below your basal metabolic rate. That's getting a little off topic though. Any other questions? I'm gonna give you one last number here and then we're gonna take a break. Okay, so like I said, hopefully we're not spending a whole lot of days in bed for 24 hours. We are getting up and moving around. So we have to add to this our resting metabolic rate plus ADLs, which stands for activities of daily living. So this just means going to work, going to school, whatever you do in a typical day. If you have a very labor-intensive job, this will add a lot of calories. If you have a very sedentary job, this won't add very much. Okay? This does not include exercise. Exercise is on top of this. So that would be total energy expenditure. Total energy expenditure includes resting metabolic rate, activities of daily living, exercise, thermal effective food, the digestion process, all other things. Okay, so we're just talking about activities of daily living. Average RMR plus ADLs is 1,800 to 3,000 calories a day. Which is why all of our nutrition labels are based on 2,000 calories a day. Because that's right in the middle of this range for the average person. These are numbers you need to know. Ranges for average basal metabolic rate, resting metabolic rate plus ADLs, and what the requirements were for measuring basal metabolic rate. Sleeping 8 hours, fasting 12 hours. All right, let's take a break. It's 5:15, let's go back at 5:20, please.
You said sleep 8 hours, fast for 12 hours.
And then supine and then lift thermoregulator. Meditate, yeah, you wanna slow down all your body parts than you do right now. What are you gonna feel?
More tired.
Give me more detail. Probably your breathing rate is elevated, you're sweating, your heart rate is elevated, okay? But you're sitting in your chair. All you need is 3.5 mLs per kg per minute, just like you did before the run. But all of those things are elevated because your body is still in transition from the run back to rest. So in that situation, you're actually taking in more oxygen than you need. Because all you need is 3.5, but you're breathing in excess of that. Okay, so we're gonna talk about the relationship between how much oxygen your body requires and how much oxygen you're actually consuming, and how they relate to each other as we transition in and out of exercise. Okay, so this is gonna be a graph. The x-axis on this graph is going to be time in minutes. Time's passing. It's not intensity here. If this was intensity, that would mean when we went outside to run, I asked you to start at 4 miles per hour and then go 5 miles per hour and then 6 miles per hour and then 7 miles per hour. That's not what I said. You're maintaining whatever speed you choose, and time is passing as you're running. On the y-axis, we're looking at the volume of oxygen. I'm going to draw one line for how much oxygen you require and another line for how much oxygen you actually consume. Okay, so let's say for the first few minutes you're just sitting in your chair. Is oxygen consumption 0? No, it's 3.5. So let's say this is 3.5, this is in mLs per kg per minute. You're sitting in your chair for a few minutes, and then you start running. Let's say you're running 6 miles per hour. Can we calculate the VO2 for that?
Yes.
We can plug into the formula and figure out the VO2. I don't know what it is off the top of my head, let's just put it right here. Your holding that speed for several minutes, and then you sit back down in your chair. As soon as you sit back down in your chair, your oxygen requirement drops back down to 3.5. Okay, so this line represents oxygen requirement. Right here is where you started exercising. And right here is where you stopped exercising. So before and after the exercise, your oxygen requirement was resting levels, 3.5 mLs per kg per minute. During your exercise, it's whatever speed you were running at. That was your oxygen requirement. We okay so far? Okay. Now I'm gonna draw a line for what your body actually consumes. So, sitting in your chair before we run at rest, everybody said you feel like you're getting enough oxygen? Okay, so these lines will be equal. I'm gonna draw it a little bit under so you can see it, but they're the same. As soon as you started running, your requirement went up, but it takes some time for your actual consumption to get up to that level. Hopefully at some point, you'll reach your oxygen requirement, you'll be getting enough oxygen. As soon as you sit down, your requirement for oxygen drops back down to 3.5, but it takes time for your body to transition back to that level. Okay, so this line represents oxygen consumption. Okay, so this section right here, requirement for oxygen is higher than your consumption, meaning you're not getting enough oxygen. This is called oxygen deficit. You're not getting enough oxygen. So I'm going to say oxygen requirement is greater than oxygen consumption. You can also say oxygen consumption is less than oxygen requirement. Both are true. This is anaerobic. It has to be anaerobic because you're not getting enough oxygen to sustain that intensity of exercise. So you have to be working anaerobically. This is uncomfortable. Here, what's happening?
Read the requirement.
The oxygen requirement and the oxygen consumption are equal. You're getting enough oxygen here. This is called steady state. Oxygen requirement equals oxygen consumption. This is comfortable, this is aerobic. You'll be aerobic here. What's happening here?
We're in a deficit.
This isn't a deficit, this is a surplus. Consumption is higher than requirement. Remember I said after you run, you're sitting down. The requirement is 3.5, but you're breathing more than that. Because you're transitioning out of the exercise. This is called EPOC. EPOC stands for excess, post-exercise, oxygen consumption. Excess post-exercise oxygen consumption. Excess meaning more than you need. Post-exercise meaning after you've exercised. Oxygen consumption. So you're after you stop exercising, you're consuming more oxygen than you need. That's exactly what's happening there. So we can say oxygen requirement is less than oxygen consumption. We can say oxygen consumption is greater than oxygen requirement. Same thing. Questions so far? Okay. Notice the size of the deficit and the size of the EPOC are very similar. You're in EPOC because you are in deficit. The bigger the deficit you create, the bigger the EPOC you create. Because in the EPOC, you've got to fix all the problems you caused in deficit. So if we think about this, if you're working anaerobically here, you're producing lactic acid. Lactic acid has hydrogen that needs to be cleared. That hydrogen is being picked up by the bicarbonate buffer and producing carbon dioxide. That needs to be cleared. Your body temperature is increasing. That needs to be fixed. Your blood pH is dropping because of the hydrogen. That needs to be fixed. So that's what you're doing in EPOC. Okay? So during EPOC, we need to clear the lactic acid. We need to clear the hydrogen, which goes along with the lactic acid. We need to clear the carbon dioxide, which is coming from the buffer, because it's picking up the hydrogen. We need to restore our temperature. We need to restore our blood pH. So the more significant those conditions are that you created during deficit, the more significant your EPOC will be. This deficit is why a lot of people don't like running. If you try to drag your non-runner friend out, we're just gonna do 2 miles. You can do it. We'll be okay. And they get 2 minutes in and they say, no, I hate running. It's so uncomfortable. I'm just gonna walk. I'll meet you at the end. They're here. What they don't realize is it takes about 3 minutes to hit steady state. If you can tolerate this discomfort after about 3 minutes, once you're in steady state, you're aerobic, you're comfortable, you can go. Long term, nothing's gonna stop you here. But you gotta get past this discomfort. Once you're in steady state, there's no problems. The other way you can alleviate that is by doing a warm-up. We didn't do a warm-up here. We just went from sitting to running. If we do a warm-up, on the same graph, if I'm drawing a line again for oxygen requirement, we're sitting, and then we start walking, and then we start a slow jog. It's gonna be a gradual increase, and then we hold our running intensity, and then we do a cool down, okay? Then our oxygen consumption is gonna more closely match that. Less of a deficit, less of an EPOC. Way more comfortable on both ends. That's a better idea.
That's what the warm up and a cool down.
So the warm up and a cool down. And so your body, you're doing with your body what you can actually more closely match. Go ahead.
So, if you're running, you'll be in a steady state until you stop, and that's when you fall into EPOC?
So that's a great question. I'm glad you said that. So the only way you can reach steady state is if you are working at an aerobic intensity. That means below your lactate threshold. I mentioned lactate threshold last week, didn't I?
Yeah.
Okay. So if you're above your lactate threshold, you're working anaerobically, so you can't be in steady state. So if your friend gets 5 minutes in and they're still uncomfortable, their muscles are burning and they're out of breath, they're going too fast. They're above their lactate threshold. They need to slow down. If you're below your lactate threshold, you'll hit steady state within about 3 minutes. So that's an important thing to understand. You gotta look for those clues that maybe your pace is too fast for them. They need to go at a slower pace, and then they'll be able to they'll hit steady state and be comfortable. But so you're only gonna have an EPOC if you created the deficit. So if you do a warm up and a cool down, there's not much of an EPOC. If you do a steady state run, you're not out of breath at the end. Check on that for you guys who run. You're out of breath at the end if you sprint the last 100 meters, or you go up a hill, because that becomes anaerobic. If you're doing a steady state run where you're keeping the whole pace the whole time, and you're aerobic and you're comfortable and you stop, you're not out of breath. There's no EPOC, because there's no deficit. Go ahead.
So in this example for the warm up and cool down, you're technically at a steady state the entire time?
Yeah, you can say
Okay.
that. Go ahead.
So on that side of the graph, would you count that as someone who's more trained?
No. You're just doing a warm-up and a cool down.
Okay.
Doesn't matter if you're trained or not. This, if you have a deficit here, it doesn't mean you're untrained. It just means you didn't warm up.
Skip the cool down, you don't create a whip. Like, you don't create that slope on the backside.
You
just
would.
drop cold.
You would have a
create
little, if you didn't do a cool down.
Even
Yeah.
without the O2 deficit.
Yeah.
you
Yeah, if you did a warm up and no cool down, this black line would drop like this. And that red line would stay the same. Yeah, so deficit is not always bad. Sometimes we create deficit on purpose. Like if you're doing high intensity interval training. You work really, really hard and then you recover, and you work really, really hard and then you recover. If we drew a graph of that, okay, the line I'm drawing right now is for oxygen requirement. You sit for a few minutes, and then you work at a really, really high intensity. And then you do a little bit of recovery, and then a really, really high intensity, and then recover, and then really, really high intensity and recover, and you can keep doing those for however long you want. Here's your consumption. You purposely created all of this deficit. And you're gonna get a huge epoch after it. People do that on purpose because if you do very high intensity intervals, you can raise your metabolic rate for 24 hours after your workout. People do that on purpose. So deficit is not bad. It just means you're working anaerobically, which sometimes is the goal. But you should be able to read a graph like this and say, here we're in deficit, here we're actually in a little bit of epoch during the recovery, right? If you do a high intensity interval during your recovery, you're breathing rapidly, and then you go again, and then during your recovery, you're breathing rapidly. So you're going back and forth. Deficit, epoch, deficit, epoch. Okay, any questions on the concept, the graph, the terminology? Okay, you need to be able to draw and label this one, not so much the other ones. I just want to make sure you understand the concept of how to read the graph. This is the one I'm more likely to ask you to draw and label. Yes?
If someone was more highly trained, would it still be the same? Or would they have less of a deficit?
They would not have less of a deficit if they did the same thing. What a more trained person would be able to do would be at a higher intensity and be able to hit steady state. Like an untrained person, if they tried to go to run at a higher intensity, they'd never hit steady state because they're above their lactate threshold. A trained person could be up at this intensity and still hit steady state. And that has to do with lactate threshold, which I'm going into next.
When you want us to draw and label this, like, in the test, would you also want us to have the epoch, what's going on in epoch?
Yes,
Okay.
and labeling the line for oxygen requirement, oxygen consumption, naming these three sections, and the relationship between requirement and consumption in the three stages. All right, let's talk a little bit more about lactate threshold. Anybody remember the definition for lactate threshold? The point at which,
We get to
that's
accumulate.
crossover.
I wish lactic acid begins to
The
accumulate.
point at which lactic acid begins to accumulate as exercise intensity increases. Okay, so on the x-axis we had intensity. Okay, you guys are confusing the lactate threshold with the crossover concept. They are related, but they're not the same. So this is, if you're at low intensity, you're still producing some lactic acid. Okay, we're always producing some lactic acid, but we have all those 6 pathways where we can clear it. So at low and moderate intensity, we're clearing it as soon as it's produced so it's not accumulating. Okay, so the line stays pretty flat. but you're increasing your intensity, right? 3 miles per hour, 4 miles per hour, 5 miles per hour, 6 miles per hour. This is what I was having you do on your treadmill assignment. At some point, you do that last bump up of intensity and something shifts. Now you start to feel the lactic acid accumulation, you start to notice your breathing rate increase, you hit your lactate threshold. If you keep increasing your intensity, let's say that happened to you at 6 miles per hour, but you keep going 7 miles per hour, 8 miles per hour, 9 miles per hour, it's gonna get worse and worse, right? The higher your intensity, the faster you're producing lactic acid, the more fatigue you're gonna feel. Okay, so this is increasing intensity. If you continue increasing intensity, there's a huge increase in lactic acid accumulation. Okay, so lactate threshold is the point at which lactic acid begins to accumulate as you're increasing your exercise intensity. We talked about how everything below that intensity is primarily aerobic. Anything above that intensity is where you start to rely more on your anaerobic systems, which is where it relates to the crossover concept because this forces us into carbohydrates. So, notice what intensity this happens at. Moderate intensity. The average untrained person hits their lactate threshold at about 50% of their VO2 max. Average untrained person hits their lactate threshold at about 50% of their VO2 max. So, let's think about this. What's a typical VO2 max for an untrained young woman? 40 mLs per kg per minute. So let's say we have an untrained young woman, her VO2 max is 40, and because she's untrained, her lactate threshold is at 50% of that. What's 50% of 40? Okay, so she's gonna hit her lactate threshold at 20 mLs per kg per minute. Could we calculate what speed that is on a treadmill? We could. Plug that in for VO2, put 0 as the grade, solve for speed. Okay, I'm not gonna go through that calculation right now, but this is not very fast. This is maybe 4 miles per hour, 4.5. So this untrained woman is not gonna like running very much because it's above her lactate threshold, it's gonna be uncomfortable. But with training, you can increase your lactate threshold. A trained person might have their lactate threshold at 60% of their VO2 max or 70% of their VO2 max. So if we do that, let's say she hits her lactate threshold at 60% of her VO2 max. What's 60% of 40?
24.
Okay, now she's hitting it at 24. It's a little better. Let's say she increases her lactate threshold to 70% of her VO2 max. Now what's she at? 28 mLs per kg per minute. That's better. Now she can probably do a 12-minute mile comfortably. Does that make sense to you? Okay, but the same training that increases your lactate threshold, which I'm going to get to in a minute, will also increase your VO2 max. It would be very unusual to see someone increasing their lactate threshold without increasing their VO2 max. So let's say she was doing all this training, she actually increased her VO2 max to 50 and increased her lactate threshold to 70% of it. What's 70% of 50? 35. Now she can run. Yes?
At what point would she be considered trained? Like the 50, right? Or because it can keep going, right?
So, on average, you can only expect to increase your VO2 max by about 20%. So, I would say someone who starts out at 40 won't get much higher than 50.
So this will be considered trained?
That would be considered trained. But we can keep increasing the lactate threshold. Okay, so let's talk about how we increase the lactate threshold. There are two ways to increase lactate threshold. Let's revisit what's happening when you hit lactate threshold first. You're hitting lactate threshold because you're producing lactic acid faster than you can clear it. Okay, let me say that again. You're hitting lactate threshold because you're producing lactic acid faster than you can clear it. So the two ways of solving that problem are either to get better at clearing it, clear lactic acid faster, or reduce your production of it. Reduce less lactic acid. So, in order to get faster at clearing lactic acid, our primary method of clearing lactic acid is the bicarbonate buffer. Okay, we talked about 6 different ways to clear it. Primary way to clear it is through the bicarbonate buffer. So if we want to get faster at clearing it, we need to convince our body to produce more bicarbonate buffer. Increase bicarbonate buffer. I also kind of have a rule, anytime you mention the bicarbonate buffer, you should write it out. It's worth a point on your test. So how do I write out the buffer?
HCO3.
Okay, HCO3 is the buffer itself. What does it pick up?
H plus.
Okay, from the lactic acid becomes
H2CO3.
2CO3, which is called
Carbonic acid.
carbonic acid, splits into
H2, H2O, CO2.
CO2. So, in order to convince your body to produce more bicarbonate buffer, you have to use that pathway. If you want your body to adapt to something, you have to challenge it. If you never challenge your bicarbonate buffer pathway, why would it adapt? So if you want to trigger your body to produce more bicarbonate buffer, you need to use your bicarbonate buffer. You do that by working above your lactate threshold, right? If you're working at low to moderate intensity below your lactate threshold, you don't need the buffer much. Above your lactate threshold is when you're using the buffer a lot. So you have to exercise at a high intensity above your lactate threshold. When you do that, you can't sustain that intensity very long because we're going to fatigue. So you have to do it in intervals. High intensity, recover. High intensity, recover. High intensity, recover. This is high intensity interval training. It's anaerobic training above your lactate threshold. High intensity interval training. It's not HITT, it's HIIT, high intensity interval training. When you train that way, your body responds by producing more bicarbonate buffer. Then you're able to clear the lactic acid faster. So what that's going to do is, maybe before you were hitting your lactate threshold at 5 miles per hour, you're producing lactic acid faster than you can clear it. Now you're better at clearing it. So you can maybe now go all the way to 6 miles per hour before you hit your lactate threshold. You've increased your lactate threshold. Questions on that? Okay. To produce less lactic acid, we have to look at why lactic acid was being produced in the first place. And I use abbreviations here. It's pyruvate, HLA is lactic acid. Why does lactic acid get produced?
A decrease in mitochondria.
Mitochondria was full, so the NADH had to reduce the pyruvate, creating lactate. So if you want to stop that from happening or slow it down from happening, you need to remodel the women's bathroom at the Staples Center so that there are plenty of stalls for everyone. You need to grow more mitochondria. Make your mitochondria bigger so you can accommodate more hydrogen. The way you do that is through aerobic endurance training, because that challenges your aerobic pathways. So, you've got to train at or below your lactate threshold, low to moderate intensity, and that you hold for a long duration. Okay, this is aerobic endurance training.
Which one's more efficient? Which one clears it, like, helps better, increases it better?
They're both very effective. Aerobic endurance training will increase your mitochondrial density. Allowing the mitochondria to accommodate more hydrogen and therefore decreasing lactic acid production. So what that's gonna do, maybe before you were training, you were hitting lactate threshold at 5 miles per hour. Because your mitochondria couldn't accommodate hydrogen any faster. Now you've done endurance training, you can accommodate hydrogen all the way up until 6 miles per hour. Okay? What that means is you can be aerobic at a higher intensity. The benefit of having a high lactate threshold is it allows you to be aerobic at a higher intensity. Okay? So before, the fastest I could sustain was 5 miles per hour. Now the fastest I can sustain is 6 miles per hour or 7 miles per hour. That's a benefit for your endurance performance. It's not going to affect your sprint performance. Okay? Your sprint performance, your intensity for your sprint is up here. If you're running 15 miles an hour, it makes no difference at what speed you shift from aerobic to anaerobic, because you're all the way up here. So your lactate threshold does not affect your sprint performance. It affects your endurance performance. So if you're racing in a 5K, 5K is about 3 miles. The person who wins the 5K is the person who can sustain the fastest speed for 15, 20 minutes. That depends on your lactate threshold. Whoever has the highest lactate threshold is going to be comfortable at the fastest speed, is going to win the race. So it's for endurance performance. Yes?
What if you want to do is create sprint endurance?
If you want to create sprint endurance,
Yeah.
can you explain to me what you mean by sprint endurance?
I would say you've got like I'm just thinking about like a soccer player who's playing like multiple games per day or something. That sort of-
Okay, so you're talking about a sport that goes in and out of systems.
Okay.
So you need to train all the systems.
Gotcha.
Yeah, and also fuel in between the games and electrolytes in between the games. So, to improve endurance performance the most, you need to do both types of training. My son, who I've talked about in here before he ran cross country all his life, distance. So he used to come home from practice and say, "Mom, I'm a distance runner. Why are we doing sprints in practice?" Well, you see, son, what's happening is, should endurance athletes be doing sprint training? Absolutely. They should also be doing endurance training, because the thing that benefits them the most is having a high lactate threshold. It's like if someone said to you, "I want to lose weight. Should I eat less or should I move more?" The answer is yes. You should do both, right? If you just work on one side of it, you might see some improvement. If you just work on the other side, you might see some improvement. But if you work on both sides, that's when you get the most improvement. So same thing here. Both of these strategies have the same result, but they're working on either end. One is working on the production end, one is working on the clearing end. So best idea is to work on both. Questions on that? Okay, that is finally the end of chapter 5. End of chapter, that was a big one, because I spend way too much time on that. So now we're going to jump into chapter 6, which is fatigue, and this one will be quick. So what comes to mind for you when I say the word fatigue?
Cardio.
Being sore?
You can fatigue during weightlifting too.
Would soreness count as like fatigue?
No, soreness is what happens the next day. Fatigue is what happens during
School.
the acute exercise.
Weakness.
School?
Camp 346.
That's mental fatigue. How would you describe what it feels like when you're feeling fatigued? Tired, weak. Okay, but tired, we have to distinguish. Tired, do you mean tired like sleepy, I want to take a nap tired?
Possibly. Possibly.
Or weak like you're having trouble contracting your muscles. Okay, so it might come with a burning sensation, it might not. Depends on the cause of fatigue. So basically when we're talking about fatigue, we're talking about you're trying to maintain a certain intensity, but you're having trouble. It's getting harder and harder to maintain your intensity. Fatigue is not the same thing as failure. In muscle failure, you absolutely cannot do that contraction again. In fatigue, it's getting harder. And that difference will make more sense as we get into this. So there are two major causes of fatigue. One of them is metabolic byproducts, and the other one is running out of a substrate. So the book organizes it by types of fatigue, talks about metabolic byproducts that can cause fatigue, talks about substrates you can deplete. I'm going to organize it by metabolic system. So I'm going to go through each metabolic system and talk about what causes fatigue in each system. So it's the same exact information, I just organize it a little bit differently. Okay, so we're going to start with the ATP PCR system. Quick review. Is this aerobic or anaerobic?
Anaerobic.
Where does it occur? Sarcoplasm. Substrate.
PCR.
PCR is a substrate. Rate limiting enzyme
Creatine.
and kinase. What's your intensity when you're in the system?
Very high.
10 seconds.
Very high. Near maximal explosive in which fibers?
Type 2.
Typically in the 2X. About how long can you stay in the system? 10 to 15 seconds. Why can't you stay in the system longer? What happens? You run out of
ATP.
PCR. PCR is the substrate. You're breaking down PCR and using the energy to create ATP. When you run out of PCR, the system's done. That's the cause of fatigue in the system. PCR depletion. Most people can last somewhere between 10 and 15 seconds. I trained in this system yesterday during my Peloton class on the bike. We were sprinting as fast as we could against heavy resistance. They were 15-second intervals. I only made it about 12 seconds before I had to take all the resistance off and recover. At the end of that interval, I was not out of breath. Does that mean I wasn't working hard enough? Is there something in this system that's going to make me out of breath? What did we talk about makes you out of breath? What activates the inspiratory centers in your brain and increases your breathing rate? Oh, I might not have said this. Oh, I didn't say it. It's this.
Oh, CO2.
I forgot to say it. Sorry. Carbon dioxide. So we're expiring this to clear the hydrogen. But on its way, it's in your blood, it's going through your brain. There's a part of your brain that controls your breathing rate. I'm just going to refer to it as the inspiratory centers in your brain. Carbon dioxide activates the inspiratory centers in your brain to increase your breathing rate. So this is why, remember at the very beginning of the semester, I said if you are sprinting up stairs with a backpack on, your muscles or your legs are burning and you're out of breath, those two things always go together. Anytime your muscles are burning, you will always be out of breath. Because the burning is from the lactic acid, and the breathlessness is from the carbon dioxide, from clearing the lactic acid. So those two things always go together. Okay? So, if your muscles are burning and you're breathing rapidly, what system are you in? What system creates lactic acid? Glycolysis creates lactic acid. That's not produced in this system. There's nothing in the ATP PCR system that makes you out of breath. The only other thing that increases your breathing rate is epinephrine. Not a whole lot of epinephrine secretion in this system either. So I did an all-out interval, worked as hard as I could for 12 seconds, and I was not out of breath at the end because I was in the system. But they only gave us about 30 seconds to rest before we went again. And then 30 seconds to rest, and then we went again. After all the subsequent intervals, I was out of breath. What happened?
You're not 35 minutes to recover.
I didn't completely recover my PCR, so my next sprints were in glycolysis. So I was out of breath. Okay, being out of breath is a clue that you're in glycolysis, because it's coming from the carbon dioxide primarily, from the bicarbonate buffer from the lactic acid.
So if you did that kind of workout over and over again, could you increase the PCR system?
No. And we're going to talk about that at the end of the semester when we talk about training adaptations. No. Go ahead.
So you're saying a 10-second sprint, like full on out, you shouldn't be out of breath after.
If you do one 10-second sprint at your top speed, you will not be out of breath after it. Try it. Make sure you're warm. Make sure it's all out. Because here's the thing. If your top speed is 15 miles per hour, but you sprint at 13, you're in glycolysis. Because you don't need your 2x fibers to do 13. You need your 2x fibers to do 15. So it has to be an all-out sprint to get you to that system. Go ahead.
So if you're going to 13 to 15 and so you're at 15, is that basically your VO2 max?
No.
Okay.
You'll actually be above your VO2 max during an all-out sprint.
Oh, right.
Yeah, because you're working anaerobically.
Okay.
Go ahead.
What part of the brain is activated with CO2?
I just call it the inspiratory centers. I think it's the hippocampus. Anybody know? You know? Okay, so that's it for the system. Deplete your PCR, system's done. If I had 3 minutes of rest in between each of those intervals, I could have done them all in the system, but I didn't. Okay, next system, glycolysis. By the way, if you supplement creatine, or know someone who supplements creatine, that's where this goes. If you supplement creatine, it increases your PCR storage. So that might give you an extra couple seconds in this system, because it's increasing your PCR storage. But only if you're working hard enough to be in this system. If you're not working at your highest intensity, it's not going to benefit you, but it might give you an extra couple seconds. Or if you're doing heavy weightlifting, to be in this system for heavy weightlifting, you have to be lifting heavy enough to not be able to do like more than 3 reps. So not choosing to stop after the 3rd rep, but stopping because you fail on the 4th, that's how heavy it is to be in this system. Supplementing with creatine might get you an extra rep at that weight. So it doesn't go directly to building muscle, it goes to helping you do the heavy work that can lead to building muscle.
Is there any way to train the system to decrease depletion?
Training the system does not decrease depletion or increase storage. We're going to talk about benefits of training the system after the second year. All right, back to glycolysis. Aerobic or anaerobic?
Anaerobic.
Glycolysis itself is considered anaerobic, although it can feed into the aerobic system. Where does it take place?
In the sarcoplasm.
Okay, rate limiting enzyme,
Phospho.
substrate.
Glucose 6-phosphate.
So yes, it's carbohydrates in the form of glucose 6-phosphate. We haven't talked about how long we can stay in this system yet. We'll do that in a minute. Byproduct in this system. Lactic acid is the byproduct in the system. Did we have any byproducts in the ATP PCR system? We did not. But in glycolysis, we have lactic acid as a byproduct. Lactic acid does not cause fatigue, but the hydrogen in the lactic acid causes fatigue. Okay, so there's actually 2 things in glycolysis that cause fatigue. One of them is hydrogen accumulation. That hydrogen is coming from the lactic acid. But if you go into 446 and say lactic acid causes fatigue, you're gonna get your head bitten off. They don't like that. Lactic acid does not cause fatigue. Hydrogen causes fatigue. The other thing that causes fatigue in glycolysis is inorganic phosphate accumulation. Where do you think that inorganic phosphate is coming from?
From the muscle.
From what reaction? What reaction produces phosphate or releases phosphate?
The breakdown of ATP?
The breakdown of ATP releases phosphate. So, if we're exercising at a high intensity, we're breaking down a lot of ATP, there's a lot of phosphate accumulating. That's gonna cause problems. Okay. Hydrogen accumulation causes fatigue in 3 ways. One of them is by decreasing blood pH. Hydrogen makes your blood acidic. The more acidic your blood is, the lower the pH. So that hydrogen accumulation makes your blood acidic. The problem with a decreased blood pH is that it inhibits PFK. What does PFK control?
The rate of, okay.
The rate of glycolysis. So if we inhibit PFK, what does that do to glycolysis?
Slows down.
Slows glycolysis. What is the purpose of glycolysis? Same purpose of all of our energy systems.
Create ATP.
To create ATP. So if we slow down glycolysis, we decrease ATP production. What is the role of ATP in muscle contraction?
For power strokes.
Lengthen head.
We're in rigor state. We need the ATP to come in and bind to the myosin head
To release it.
to release. And then we break down the ATP, come back up to 90 degrees, and then we can cross bridge and power stroke again. If we slow down our ATP production, we've got to wait before we can do the next power stroke. So it's interrupting your muscle contraction. It's going to slow down your muscle contraction. What that feels like to you when you're running on the treadmill or lifting your weights is it's getting really, really difficult to do this. Okay, I'm just going to put it's interrupting muscle contraction, but you should understand how a decrease in ATP production would interrupt muscle contraction. Anything that interrupts muscle contraction is causing fatigue by definition. That's what fatigue is. You're having trouble contracting your muscles. Questions on that?
So for decreasing ATP production, so at the point, let's say I'm like curling like a 30-pound dumbbell and I'm struggling lifting it, that's that decrease in ATP
That's
production?
one of the things that's happening. There's a lot of things happening here. That's one of them. Yep. All right, another way hydrogen causes fatigue is also through the decrease in blood pH. This time, it's inhibiting a different enzyme. Decrease in blood pH also inhibits glycogen phosphorylase. Glycogen phosphorylase controls what process?
Breakdown.
Glycogenolysis, breaking down glycogen into glucose. Okay, we're talking about specifically from the liver, glycogen into glucose. So if we inhibit glycogen phosphorylase, we're slowing down glycogenolysis, which decreases glucose production. Because the liver glycogen is where we're getting most of our glucose. And we know that liver glycogen typically goes to glucose, which becomes our G6P. So if we're producing less glucose, we're producing less G6P. Got less G6P available. We know that high levels of G6P activate PFK. What do you think low levels of G6P do? Inhibit PFK. So if we have less G6P, we're going to inhibit PFK. What happens if we inhibit PFK? We slow glycolysis. And then what? Decrease ATP production, which interrupts muscle contraction, which causes fatigue. These are two different ways that hydrogen causes fatigue. They do overlap, but you need to understand both of them. Yes?
Is it decrease in ATP production or slower, ATP production?
Same thing.
Same thing?
Yeah. Questions? Okay, make sure you don't forget the decreased blood pH part, because I get a lot of people saying hydrogen inhibits PFK. Hydrogen doesn't directly inhibit PFK. Hydrogen decreases blood pH, which inhibits PFK. Okay, another way that hydrogen causes fatigue is that hydrogen likes to bind to troponin. What do we usually have binding to troponin?
Calcium
Calcium. And what happens when calcium binds to troponin?
pulls tropomyosin.
Opens the binding site so we can cross bridge and power stroke. If hydrogen binds to troponin, that doesn't happen. Binding sites stay covered. So, if you're exercising at a high intensity and there's a lot of hydrogen present, the troponin has a choice. It's got hydrogen, it's got calcium. It gets to choose which one it wants to bind to. What do you think it will choose? It will choose hydrogen. Troponin has a stronger affinity for hydrogen and it prefers it. So if there's a choice, if there's hydrogen present, the troponin will bind to the hydrogen. If hydrogen binds troponin, the troponin does not pull the tropomyosin off the binding site stays covered, blocking the cross bridge, blocking the power stroke. Really, really hard to create muscle contraction when that's happening. Okay, the binding sites are physically blocked. This is called competitive inhibition. Competitive inhibition. Competitive because the hydrogen is competing with calcium to bind to troponin. Inhibition because the hydrogen will win and it will block muscle contraction. Any questions on that one? Okay, so that's 3 ways that hydrogen causes fatigue. Let's talk about how the phosphate causes fatigue. So the problem with the phosphate accumulation is that it inhibits the calcium release from the sarcoplasmic reticulum. Phosphate accumulation inhibits the calcium release from the sarcoplasmic reticulum. What is the role of calcium in muscle contraction? We need it to bind to troponin to open the binding site. If we're breaking down a lot of ATP, high intensity exercise, phosphates accumulating, less calcium is going to be released from the sarcoplasmic reticulum. If there's less calcium available to open the binding sites, fewer binding sites, fewer cross bridges, fewer power strokes, gets very difficult to contract your muscles. That is fatigue. Okay, so less calcium availability, fewer cross bridges, fewer power strokes, fatigue. So keep in mind, all of these things are happening at the same time. Okay, this is not a process with step 1, step 2, step 3. If you're exercising at a high intensity, you're producing lactic acid, which is causing hydrogen accumulation, which is causing all of these things. At the same time, you're breaking down a lot of ATP, accumulating the phosphate, causing this. So all of this is happening at the same time. So if you're exercising at a high intensity, not only do you have less calcium available, but the calcium that is available has to compete with the hydrogen for the binding sites. So you can imagine the more intense these conditions are, the harder and harder it's going to be for you to maintain your intensity. Questions on that? Okay, so you need to be able to explain back to me causes of fatigue in anaerobic glycolysis at this level of detail. Let's talk about how long we can stay in this system. What do you think about this? How long do you think you can stay in this system? Throw out some numbers.
3 minutes.
3 minutes?
I can do it in 10 minutes.
10 minutes? All right.
Hour.
An hour? All right. So let's make this more realistic. Let's think of an activity that would put us in glycolysis. How do you know if you're in glycolysis? Your muscles are burning and you're breathing rapidly. So think of an activity that would cause that to happen.
Jump stairs.
Swimming.
Okay, so something like swimming. Swimming can be done in any of the systems, right? We can do an all-out sprint and be in the ATP PCR system. We can do a slow crawl, be in the aerobic system. So let's pick something that is for sure going to put all of us in glycolysis.
400-meter run.
Okay. If we're sprinting it as fast as we can, Stairmaster depends how fast we go.
Jump roping.
Some people can jump rope for a really long time.
Basketball game?
Basketball game, you're going in and out of.
You hold
Jump
the squat.
squats are a great example.
Jump squats.
And everybody would agree that doing squat jumps will make you out of breath and legs burning.
Yes.
No?
I wouldn't even try it.
I'm gonna give you a weight vest. How long do you think you can do squat jumps for?
8 to 12.
5 to 8
12
reps.
5 to 8 reps. So 5 seconds?
10.
A minute? What do you think?
Like 8 to 12 reps.
8 to 12 reps? Okay, come on up.
Like body weight.
Come on up. Yeah, come on up.
I got leg day in like an hour.
Oh. Michael, come on up.
My calves are sore. I was doing it.
Oh, you got Crocs on that. Come on, I need some volunteers. Right here.
Might as well get a warm up.
Might as well get a walk. They're just wimpy air squats.
We need a girl.
You can do it for 10 minutes.
We need a girl.
How about a woman?
Woman.
Mm.
Give me a woman. Cassidy!
Cassidy! I don't know, my other classes had 4 volunteers.
No, she's a woman. Glasses.
Okay, I'm okay with 3. Okay, so we are actually doing this.
Regular squats?
Squat jumps.
Join Professor.
So.
Sorry.
Oh, darn. Okay. Yeah, awesome. Let's go. Okay, so on your squat, your heels have to stay on the ground. And then you're jumping, and then you're landing in your squat, and then jumping again. So it's a continuous squat, jump. You're not stopping in between. Squat, jump. You're going as long as you can. When you stop, you're done. You can't stop and rest and come back in. But it's fine. When you're done, you can stop and then just walk around again.
How low do we go?
That's up to you. It does not need to be a full squat.
This guy dropped the
Quarter squat, half squat, it's fine, and with a big jump. Thanks. Okay, give me a half squat at least. Ready? I don't know, someone in my class this morning was touching the ground on their squat. And actually, I had someone in my class this morning, nobody was here this morning, you weren't here this morning. I had a student in my class this morning doing squat to tuck. Squat to tuck. And he was like hitting the, he was like, whoo, he was crazy. Okay, tuck jump. He was doing a tuck jump. Okay, ready, go. Good, heels stay down on your squat. Big jump, soft landing. they might need some encouragement now. You guys help them out. Keep it up, keep it up. I'm sure you're feeling something now, but you can keep going. You can keep going. Don't give up. We're at 30 seconds. Go as far as you can. Big jump. Come on. Keep your jump. Keep your jump. 40 seconds. All right. You can keep walking around if you're done. Come on. 43. I'm done. 45 seconds. Nice job. All right. You guys can keep walking around. You might not want to sit down right away. So, can you guys all agree that you're in glycolysis?
Yeah.
Are your legs burning?
Yeah.
Breathing rate increased a little bit? Okay, so we made it just about to 45 seconds. So, Sam, do you want to rethink your claim that you can stay in the system for 10 minutes? You still think you can? Okay, so here's the deal though. Oh, you can? Okay. Here's the deal though. If I had given them all 20-pound weight vests, would they make it that far?
No.
But would they still be in glycolysis?
Yes.
Probably. What if I said you only have to jump every other squat? Could you have gone farther, gone longer? Probably, but still in glycolysis? Most likely, yes. So, the point is there's a wide range of intensities in glycolysis. It's not like ATP PCR where it's all out or nothing. To be in this system, this is your lactate threshold, you just have to be above your lactate threshold. And we're working in anaerobic glycolysis. Okay, so I'd estimate the squat jumps fell about right here, and we made it about 45 seconds. If I gave you a 20-pound weight vest, that brings the intensity up here. The higher the intensity, the shorter duration you can sustain. If I had you just jump every other squat, the intensity might have been here. Still above your lactate threshold in glycolysis, but not as hard as what you did. All of these are in glycolysis. So I can't put a specific number on how long you can stay in glycolysis because there's a wide range of intensities. All I can say is the higher the intensity, the shorter duration. Okay? So like I said in my sprint on the bike yesterday, when I was doing 12-second sprints, my second, third, fourth sprint were in glycolysis. But I couldn't go longer than 12 seconds. I was up here. But if you're just above your lactate threshold, you can sustain that for several minutes. Okay, so it's a wide range. Questions on that? Okay, I also want to point out that I started noticing fatigue at about 15 seconds, which is why I asked you guys to encourage them. Because motivation matters in fatigue. If I had asked them to go one at a time out to the hallway and see how long they could do squat jumps for, do you think they would have made it as long? No. No. Having people watch them and cheer them on motivates them to tolerate the discomfort a little bit longer. Okay? So as they started slowing down, if I got in Cassidy's face and said, "Cassidy, come on, give me 5 more squats," do you think she would have done it? Okay, what if I offered you guys $20 to do a couple more squats, to get all the way to a minute? You'd probably do it. What if I offered you points on the next midterm? Okay, so don't discount motivation in fatigue. You can feel fatigue and still continue. Fatigue is not the same as failure. At some point, if you continue, you will eventually hit failure, but you don't have to stop as soon as you start feeling fatigue. Okay? So I like to put it on a continuum. So if this is rest, and this is physiological failure, meaning no matter what I offer you, or how loud I yell at you, you cannot contract your muscles at that intensity anymore. That's physiological failure. Fatigue sets in right about here. Physiological fatigue. Moderate intensity. You guys felt this about 15 seconds into your squat jumps. But you didn't have to stop. You kept going. right about here is where we hit psychological failure. Meaning you give up. Okay? So you tolerated the fatigue a little bit longer, but if I motivated you the right way, you could have done more. You weren't quite all the way to physiological failure. This is where most people give up, a little bit when they start feeling fatigue. The problem is that results occur up here. If you want your body to adapt, you have to challenge it. So if you give up at the slightest feeling of fatigue and discomfort, you're not going to see many results. Okay, so someone can say, I've been going to the SRC and working out 3 times a week, but I haven't gotten any stronger. I haven't seen any growth. But you go watch them work out, and they're doing bicep curls, and as soon as they start to feel some discomfort, they stop. You have to push through that discomfort, challenge yourself if you want to see adaptations. The closer you get to failure, the more results you see. Okay, so there's also an increased risk of injury up here, so you have to kind of balance how far you're willing to push yourself with how much risk you want, but you don't get a whole lot of results if you don't get into that uncomfortable zone. Questions on that? Yes?
So like physiological failure is like that point where like you cannot physically, like you're struggling with that last rep to lift that weighter.
Yeah, no matter what kind of motivation I give you, you cannot physiologically contract your muscles anymore. Yep. Which is, it's hard to get to because you have to be properly motivated to get that far. All right, that's the end of glycolysis fatigue. We just need to do aerobic fatigue. Any other questions? Aerobic fatigue will be quick. All right. We can lump all the aerobic systems together because they have the same cause of fatigue. So, what systems are we talking about that are aerobic systems?
Krebs.
Beta oxidation.
Electron transport chain. Okay. Quick review. Where do these occur? Mitochondria. Substrates. What substrates can we use in the Krebs cycle?
Or is it cytochrome oxidase?
Acetyl-CoA.
No, because that's the.
Okay, but from what source? The acetyl-CoA can come from 2 different places.
Fat or
Fat can take us into the Krebs cycle.
or C.
Carbohydrates can take us into the Krebs cycle. How about beta oxidation?
Fat.
Just fat. Electron transport chain? We can get from carbohydrates to electron transport chain and from fat through beta oxidation into the electron transport chain. Rate limiting enzymes. Krebs? Isocitrate dehydrogenase. Beta oxidation?
Lipoprotein.
Lipoprotein lipase. We have to take the fat out of storage. Electron transport chain? Cytochrome oxidase. Any metabolic byproducts in any of these systems that we talked about?
H2O.
H2O. Water is a byproduct of which system?
ETC.
Okay. Water's not a problem. Water does not cause fatigue. Water is a good thing. Any other byproducts from any of those systems that we talked about? Not as a byproduct. We didn't talk about any other byproducts from these systems. So let's look at the substrate depletion. Are we going to deplete fat? Fat is considered an unlimited resource. Even a skinny person, depleting your fat's not a thing. How about carbohydrates? Can we run out of carbohydrate storage?
Yes.
We can. So that's the cause of fatigue in this system. Glycogen depletion. Average person stores enough glycogen to sustain Moderate exercise for about 2 hours. Average person stores enough glycogen to sustain moderate activity for about 2 hours. Anybody ever run a marathon? Okay, anybody know someone who's run a marathon? How long does it take? An hour.
Like 3 hours.
There's nobody on earth who can do it in an hour and a half, sorry. Nice try. Typical person, 4 hours, 5 hours, 6 hours. How is it possible to exercise that long if they're depleting their glycogen?
They use like
You
journals.
have to take in glucose. If you've done a marathon or you've talked to someone who's done a marathon, they will tell you you have to intake glucose to be able to exercise for that long. They usually just use these goo packets that are just straight glucose. And you just have to take that to be able to exercise that long. If you've heard about people collapsing partway through the marathon, they didn't balance their glucose levels correctly, they ran out of glycogen. That's called hitting the wall. When you run out of glycogen, you just collapse.
Is that one like, they're like practically like, they don't even know what they're doing?
Yeah, they're usually delirious, throwing up, diarrhea, they just collapse and it's a big problem. And you need to manage your glucose levels. Go ahead.
So people, when they run a marathon and stuff, they usually take goo. Is that something that helps with that?
Yeah, goo is glucose. It's just straight glucose. So you don't want to have a meal that you have to digest. So you just take straight glucose. It goes into your blood and then you use it. Go ahead.
So like for extreme endurance, like if we're, at what point does protein degradation occur? Because like sometimes.
If you run out of glycogen, or when you get close to running out of glycogen, that's when protein degradation will ramp up. But we try to avoid that by taking glycogen. But what this means is, most of us are not running marathons very often or at all. If you're just going for, let's say you take your friend, your non-running friend for a run again. You've convinced them to get past the 3 minutes and they hit their steady state. They get a mile in this time. And they say, I can't do it. It's too hard. I'm too tired. You go ahead, I'll meet you at the end. What's their cause of fatigue? Did they deplete their glycogen in 1 mile? We can assume a 10-minute mile. We can assume a 12-minute mile. We can assume a 15-minute mile. It's almost a walking pace. Are they going to deplete their glycogen? Hold on 1 second. They're not going to deplete their glycogen. Are they going to have hydrogen accumulation, lactic acid? They shouldn't. If they're out of breath, what does that tell you about their pace? Their pace was too fast. They need to slow down. So we're assuming flat, not hills, because every time you go up a hill, you're going into glycolysis. So we're assuming flat, steady state pace. She's hit steady state, no cause of fatigue there. There is no physiological cause of fatigue there. She's stopping because she's bored. She needs motivation. So maybe you need to give her your AirPods so she can listen to music. Maybe you need to run at her pace and have a conversation with her. Maybe you need to offer to buy her Starbucks if she finishes the 2 miles, or give her money, or whatever. You got to figure out what motivates them. There's no physiological cause of fatigue in something like that. If their muscles are burning and they're out of breath, they're not in the aerobic system. That is not a cause of fatigue in the aerobic system. Okay, so you can't discount motivation when you're talking about fatigue. It comes into play in all of these. Questions on that? Okay, that is the end of chapter 6. So we finished chapter 5 and chapter 6 tonight. So that means you have a lot to do on the study guide, which you should definitely get done. I know you guys are on break next week, but you still got to keep up with that study guide, okay?